So apparently, the video I did introducing forces last year disappeared in the mists of time. Guess we know what time it is. So I'm going to re-establish and redo this video right now, see how things go. We're going to introduce you to the concept of forces for the regular physics class. This is in Chapter 4. Chapter 4 is on forces. And for the AP class, this is Chapter 5. Same introduction for both classes, no problem there. First thing I wanted to mention right off the bat is that what we've studied so far is referred to as kinematics. Kine is a Greek or Latin word root that means to move, and so this is a study of motion, how things move, and we decided that we needed to keep track of a bunch of different quantities, displacement, position, velocity, acceleration, time. These things could be changing, so there might be initial and final things, but it doesn't explain why things move. Why, when you shove something across the floor, why does it come to a stop, kind of thing. And that's where we have to get into dynamics. Dynamics is the question of why. And the hero of the story on dynamics is somebody you might have heard of, and that is Sir Isaac Newton. Now, Newton was an interesting dude. We could talk about him for weeks, I think. Possibly one of the smartest people on the planet over the course of time, you could argue. Certainly huge contributions to science. He was hired by the British government to help them deal with counterfeiting of the royal coins, and he's the one that came up with the idea of putting ridges in the edges of the coins like we have on our quarter. You see, people were taking the coins, which were made of a precious metal, and they were shaving the outside edge, making the coins imperceptibly smaller. But then after you shaved a number of coins, you could melt down the precious metal, recast it into a, with a form that you made. This is the counterfeiting part. And you would now have more money. And if you know anything about economics, you know that when more money shows up, it undermines the money that already existed. So it's basically like stealing from the king. The punishments for counterfeiting royal coinage were quite severe. Don't want to get into the torture discussion like Dr. Goodstein does all the time. But Newton was the one who came up with ridges on the edge of the coin, which is something we do today. One thing that I can say is that there's no evidence whatsoever that Newton was sitting in an apple orchard and an apple fell on his head. That is something that I think started in a cartoon, an educational cartoon in the 50s, and then turned into an urban legend that somehow his inspiration about gravity came from a concussion or percussive inspiration there. No, I think if I read correctly, and it's again secondhand, but in one of his journals he says, I observed an apple fall from a tree and I wondered what pulled the apple from the tree. Now that's a pretty obvious thing because everybody at the time had an idea that there was this force called gravity. In Aristotle's time, gravity was just a force that tried to return things to the center of the earth, which was their rightful place. So, but the genius of Newton is that he said, well, okay, gravity extends up out of the ground into the high branches of the tree, and when the apple gets sufficiently full of water and the stem gets sufficiently rotten, the apple falls to the ground. This is part of the apple's reproductive cycle. But his question was, well, if it extends up into the tree, does it extend any higher? And of course, rain comes out of the clouds. That's probably pulled down by gravity. Okay, does it extend as high as the moon? And this was interesting because gravity on the Earth produces straight line motion, straight down towards the center of the Earth, but the moon is going around the Earth in circular motion. And in order for gravity to take the moon and not pull it straight down and collide with the Earth, which would have happened, millions of years ago, in order for it to go in a circle, gravity needs to get weaker as it goes higher. The other part of that, of course, is a two-dimensional motion thing, that the moon has some component of its velocity to the side, and so when gravity pulls down, we wind up with this curved path. In the case of the moon, the curved path turns into a circle because it never does get closer or further. But Newton figured out that the gravity must get weaker the higher you go, and worked out a theory for gravity, and that's what he's most famous for. Okay, the other thing he's most famous for is for codifying or writing down some things that are true about forces. And we'll just start by saying that a force is a push or a pull. That's the common sense definition of a force, a push or a pull. Forces come in two flavors. There are contact forces, those that require you to touch something. And of course, human beings, we exert contact forces. If we want to exert a force on something, we have to touch it. Jedi, however, can exert non-contact or field forces, otherwise known in the time of Newton as action at a distance. And Mother Nature has a number of these action at a distance forces up her sleeve. The most notable one is gravity. That's the one you guys learn about as you're a baby. You fall down, go boom. Gravity is the first thing you learn about, but also the electrostatic force, magnetism. Magnets are fun. There's a weak nuclear and strong nuclear force, all kinds of stuff. Now, we have to exert contact forces. Nature can exert field forces, and I mentioned the Jedi. They have somehow come in control of some sort of field force that allows them to retrieve their lightsaber and cut themselves down out of the roof of a cave and slay some sort of crazy beast. I think I saw that movie once. So Newton, in codifying these ideas about force, he came up with three laws. And let me just get rid of this piece of paper. This is just me riffing. Let's do this for realsies. Okay, so Newton's three laws. I'll just put N3 up here so you'll know. And it's kind of interesting that a lot of scientists have written three laws. Kepler has three laws. There's a number of, I think Asimov in his science fiction had three laws of robotics. But law number one, an object at rest tends to remain at rest, comma, an object in motion tends to remain in motion, comma. Now, I could stop here and I would have Galileo's law of inertia. Things like to keep on doing what they're already doing. If something's at rest, it'll stay at rest. If it's moving, it'll keep moving. By the way, this line right here in Galileo's time was brand new because Aristotle thought that things that are in motion will eventually come to rest because they want to become at rest. But Newton added the next line, which is genius. Unless acted on by a force. And that's where the word force comes into play. By the way, acted is also an important word. Newton used action and force interchangeably. So whenever somebody says something about the action, it means the force. Now, I've left some words out. Unless acted on by an outside force, unless acted on by an unbalanced force. What I think is most important is that it's a force. The internal forces can't change your motion. If you're in flight, if you just jumped off a trampoline and you're in the air and you clench your ab muscles as hard as you can, it's not going to affect your motion. But if an outside force like a gust of wind or something was to hit you, then that would affect your motion. Now, number two is the only one that's an equation, and this is where he defined how forces work. F net equals m times a. That equation is the equation we're going to use quite a bit in this chapter. It's a vector equation. Force has a direction, so I'll put an arrow on top of the F. And of course, acceleration has a direction. Mass is a scalar, so the direction of the force will give you the direction of the acceleration. And what this is saying is basically that forces cause acceleration. And if you see acceleration, you can deduce that there's a net force. Now, what does this word net mean? Net means an algebraic total. First time I saw the word net, it was on the cereal box. You know, as a kid, I would eat cereal on Saturday mornings and stare at the box while I ate the cereal. This is A lot of people do this, and I don't understand why. Anyhow, it said on the front of the box net weight, and I had to ask my dad, what the heck is net weight? I imagined that they took all the boxes of cereal and piled it in a big cargo net and then strung it up and then weighed them to see how much the cereal boxes weigh. And he said, no, 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 net weight means they weigh the cereal box with the packaging and the little toy inside and the cereal, and they subtract away the known weight of the packaging and the toy inside in order to come up with the weight of the cereal. And after a little bit of thinking, I realized, okay, yeah, it's hard to weigh cereal, especially when it's already been portioned out into a box. So I get this, the net weight. You're going to encounter net when you get your first paycheck. You're going to have net pay, which means that your employer is going to promise you a certain amount of money, and then they're going to be subtracting things for the government, taxes. I have union dues subtracted from my paycheck, and so I get a lesser amount. My net pay is less than my gross pay. The final one, the final of Newton's laws, is the one that is the most subtle and most difficult to understand. And it's also the one that got stolen and used to explain a lot of social phenomenon. And that is that for every action, there is an equal and opposite reaction. I know that my parents used to say this all the time, to help explain why, because I had punched my brother, that I was going to get a spanking or something like that. That my action is going to lead to a reaction. I guess that would be what, fate or kismet or karma. But remember that Newton, when he said action, he meant a force. So for every force, there's an equal and opposite force backwards, a reaction. And that means that you cannot push on something without being pushed back. When you go to open the door, you push on the door, and the door is going to push back on you. And you may find, if you pay attention to yourself, that you are preparing for that force backwards on you by leaning forward into the door or making sure your feet are solidly on the ground or something like that, because you know that that's going to happen. I remember a very important lesson about equal and opposite reaction. In middle school, every day we ate our lunch as fast as we could. We checked out a basketball and we played half-court basketball. And we tried to carry that on into high school. But my friend Gordon, freshman year, he started to grow a lot. He got recruited by the water polo team, and he started working out every morning, weights and swimming. And by the time we got to the end of our freshman year, beginning of our sophomore year, we would go up for rebounds, and I would bounce off of Gordon. The force back as I went up for the ball, the force back on me from his body was large enough that I felt it. Not only that, but if you look at this equation, we get equal forces on each other when we go up for the rebound. We hit each other and we get an action reaction that are equal. But because his mass is so much larger, his acceleration was small. He wasn't driven off the ball. I was still barely over 100 pounds, and I would experience a huge acceleration. He would knock me out of the way and take the ball. So, it became less fun. All right, so these are Newton's laws. I'm going to need you to memorize them. You can just remember that number 1 is all about inertia plus the definition of a force. Number 2 is the equation. Number 3, action reaction. In fact, action reaction pairs is what they call these things. All right, that's good. That's the first thing we're going to do. We've got the definition of a force being a push or a pull. We've got Isaac Newton being the hero and his 3 laws that you're going to memorize for me. And now let's talk about how practically you solve these things. When you are trying to solve force problems, you are going to draw a special diagram. In addition to any other pictures you need to draw for motion reasons, you are going to draw a free body diagram. And a free body diagram is abbreviated FBD by everybody who does this. I don't need you to put the periods in there if you don't want to. I once had a lot of fun with a class. You know how I like to try to lie to people. I once told them that this was an Italian guy. His name was F. Ribati. So it was a F. Ribati free body diagram. Actually, if you say it like that, it sounds like Jesse Jackson. F. Ribati. F. Ribati, I must get along. Anyway, the free body diagram and FBD. And a free body diagram has a couple of really simple rules. Number 1 is to represent Oh, this pen stinks. Not physically, it's just making big letters. Let's do a little switcherooski here. Represent the object in question as a dot. So no matter what you're studying, you represent it as a dot. So if you say, oh, there's a car, there's a drawing of a car. If you say, here's an elevator, drawing of an elevator. Apple sitting on a table, apple. Just a dot to represent the object. We don't need to have any artistic skill. In fact, we don't want this dot to have any extent. We don't care about how big and small or the shape of the thing, just a central location. Then we put arrows away from the dot for the forces. So if I had a dot and it was an apple sitting on a table, I might say, oh, there was probably some gravity here and the table is pushing up because the apple is not falling. If I had a, airplane, when you study aerodynamics, there are the 4 forces of flight. And if the airplane was moving to the right, you would say that there's a thrust force, there's a drag force, there's lift from the wings, and then there's weight of the airplane. So arrows going away from the dot. That's the second thing you do. And then the third thing you do is you label all the forces. So on these things up here, I said the names, but I didn't write anything down. So let's just get in there and say that this would be weight. And so would this. I said this one was lift. This was somehow the table. This was thrust. That's what they call it when you have something pushing your airplane forward. And this was drag. So we have names for all these forces. Draw a dot, put the forces on it, label the forces. This is all a brainstorming technique to try to get you into thinking about forces. Now, in order to go any further, we're going to have to talk about some common forces. Forces that occur in most problems. And the most common force of all is weight. Weight is the force of gravity. And the force of gravity can be abbreviated with the letter W, or you could do a capital F with a subscript G. I really like this one because you can have all your forces be represented with an F with a subscript that tells you what kind of force it is. And the force of gravity is equal to the mass of the object times the acceleration due to gravity. Yes, the same acceleration due to gravity, 9.8 meters per second squared, that we used earlier. So whatever your mass is, and that would be in kilograms times the local acceleration due to gravity, that gives you your weight. So you can label it with a W, or you can label it with an FG, and then later when you need to calculate it, this is what it is. Another common force is the normal force. Now I know that sounds a little weird to say the normal force. Yeah, why? Because it's normally there? Yeah, normal in this case is a geometrical term, and it means perpendicular. So when something is sitting on a surface, so here's my easy button. By the way, doesn't work. These things are easy but not very well made. It's sitting on top of this table, the same table that has my paper and my hands on it, and it's not falling, even though there is a force of gravity. So the table itself must be somehow pushing upwards, somehow lifting this thing a little bit, and that force is called the normal force. And basically, it has something to do with molecular structure. The surface of the table is made of molecules. The molecules are bonded to each other in the left and right direction. And then when this easy button wants to go through the table says, no, we're not gonna separate and get out of the way for you to go through. So we're gonna have to exert some sort of sideways force. Think of it as an atomic version of Red Rover. Okay, so the normal force. Now the normal force is weird. It doesn't have a formula. You can't calculate it in advance. It's just as big as it needs to be, or needs be. That's probably better grammar. As big as it needs. Well, maybe needs to be would be better. More American to say needs to be, but whatever. It's as big as it needs to be. That means that up until the point where the molecules just can't hang together, then that surface will exert a force. I had a situation happen one time. I was sitting in an old lawn chair, you know, the kind with the woven straps, and this lawn chair had been outside for a couple of years, and I sat down, and the molecules said, no, we can't hang on to each other. We're just going to break. And I fell through the webbing with my butt, but the rest of my body was sticking out the top of the chair, so I was kind of stuck with a chair wrapped around my mid torso like a turtle shell or something. It was pretty embarrassing, and everybody at the party was laughing at me. I still remember it to this day. Another common force is the force of friction. Friction is a force that resists motion. I think we all have experience with friction, and the force of friction can be abbreviated with an F and a capital F. By the way, normal force, you could just do a letter N. That's what the AP kids will do. For the college prep kids, let's do capital F, lower or a small subscript N, and this could be that or that. And friction is very interesting because friction is equal to a coefficient times the normal force, or a coefficient times the normal force, depending on which class you're in. This coefficient, this is not the micro symbol from the metric system, but it is the same letter. It's a mu. The coefficient of friction tells you how frictiony the surface is. I think we all know that concrete and asphalt, blacktop, are more frictiony than ice. If you fell off your bike at speed onto asphalt, you would be get a set of burns on your body from that friction. But if you fell onto ice, well, the ice would be firm, but you're going to slide along and not get the friction burns from that. So we'll have to be talking about what this coefficient is. One more. Tension is a force. You can abbreviate it with a T or F with subscript T, and tension is the force in a rope or chain or, I don't know, cable, anything that's a one-dimensional object that's flexible. The reason why tension is special is that these things are used all the time to transmit forces because they only pull. They only, okay, this deserves another color. They only pull. So you don't have to guess what direction they are, just what direction is the rope going. That's the direction of the force. You can't screw that up. Finally, if you have any other force, you can give it its own symbol. So if you had a force from an engine, let's say, that was somehow driving a car forward, you could say capital F ENG. If you had a force, we had lift before from the wings, and if you were exerting force, we could have FU. I think that's pretty funny. All right, folks. That's enough for today. I did not cover the units of force, but I am a little over time on the 20 minutes. So today's video.